we discussed the Lorentz transformations. We started basically relativity theory, and what we have seen that the same principle of the same symmetry, the principle of relativity, which was used for classical mechanics, is used also in relativistic theories. The only difference is how we present this principle depends on the space-time transformations. In the classical case, we used Galilean transformation, while in relativity, we use Lorentz transformation. The Lorentz transformation led us to an new understanding, limitation of the velocity. And we found there's a universal velocity, which all the velocities are limited by this universal speed, which is the speed of light. And therefore, this enforces a new velocity addition, and we have seen that this new velocity addition solves some shortcoming that we found in classical physics. Now, this limitation tells you that the geometry became non-trivial if in classical mechanics the velocities form the three-dimensional space R3. Now they will be bounded. And in this lecture, we'll discuss consequences of this observation that we got, boundedness of the velocity, and we'll connect it with the bounded symmetric domain. I want to recall you what is called a real bounded symmetric domain. Real means over the real numbers. There are also complex bounded symmetric domains when we are talking about the complex numbers. So a real bounded symmetric domain is a domain in a real Banach space. In our case, it will be R3. We denote out D, the collection of homomorphisms, which are smooth bijections, one-to-one map from D to D. What do you mean by smooth? Smooth will use two types of smoothness, either projective, preserving only line segments. That means you have a line segment before the transformation, after the transformation, it will be still a line segment, or conformal, preserving angles. Any geometry mostly discussing what are line segments and angles, if you preserve both of them, you'll get only trivial transformations which are not enough to be, not wide enough to define bounded symmetric domain. So we have to give up something. Projective transformation give up on the angles, and they preserve only segments, while conformal keep the angles, but lose a line is no more a straight line, a line segment is no more a line segment after the transformation. A domain is called symmetric if for any element A in the domain, there is a symmetry, SA belonging to the out D, that means it is a bijection of D. Symmetry means that the square of it is the identity and fixes only the point A. That's the definition of a symmetric domain. If it is bounded also, then we have a bounded symmetric domain. There is a theorem which tells you that a domain is symmetric. You need to ask on a symmetry about one point, and homogeneity in the following sense, that if you have 2 points in the domain, there is automorphism, that is much more a bijection, that takes point Z into W, to the other point. That means all the points can be mapped one to other by bijections belonging to the out D. So that's the definition of the bounded symmetric domain over the real number. Now let's understand how we'll get what kind of geometry is on the velocity ball. So we're talking about in relativity, the velocities are bounded by the speed of light. It means we have a bounded domain. And here we'll get how we'll see that the maps are projective maps. That means they take a line segment into a line segment. To do this, we have to do the following. We have to, first of all, to embed the velocity into a walled line with this velocity b. Let me see it as the time, and vt is the space increment. We denote this line by L. Here on the graph, you have this line. Then we take a plane pi at t equals 1. This is the t-axis. T equals 1, this plane pi. And what it happens when you take t equals 1, so the value at the intersection of this line with the plane is 1 and b. So 1 will be always, because we took the plane t equals 1. And here we have the velocity. So we have association of any line going through the origin with a velocity in this way. The ball of admissible velocities, d, is this one that you see it here, is the sum all the v's which are less, v square is less than c. That means the velocity is bounded by the speed of light. I choose units of time to be equal to c, so 1 is the same as 1 here, which is c. The Lorentz transformation that we discussed that are in the previous lecture, they map the velocity ball into the velocity ball, because under the Lorentz transformation, we have said the metric is preserved and the speed c is invariant. That means everything which was less than the speed of c will remain within the speed of c. Obviously, such a transformation is a bijective because we can go from the second system to the first one by inverse. So it is invertible, and onto anything which was in the second system is image of something from the first system. Now how we get an interval AB in this ball. So we do the following. We take some plane through this interval and the origin. The two-dimensional plane, we call this plane Q. This Q is a two-dimensional plane through the interval AB in D. This interval is in the velocity ball and the origin. What is doing lambda? Lambda is a linear map. Maps a plane, a two-dimensional plane. In a two-dimensional plane, Q prime. L will be some L prime, which is still in the plane, because if you are in a plane, after the transformation, you're still in the plane. So the velocity will be still in this Q prime. And Q prime, so AB, which is the intersection of Q with the plane pi, will be now once more the intersection of the plane Q prime with pi, which is another interval, A prime, B prime. That means after the transformations, Lorentz transformation on this domain, take an interval into an interval. So we get very good description what kind geometry is preserved, the geometry preserving line segment. So automorphism preserves line intervals, and therefore, by definition, this is the projective geometry. What are the projective maps? How we can, this is the A, O plus B is Einstein's velocity addition. That means if we have a velocity v in system K prime, and the system K prime moves with the velocity A, Then in system K, you get VO plus V, which was the formula for Einstein's velocity addition. How it looks like. We have seen that lines goes to lines. So if you take a mesh, equally spreaded lines, two direction, and you see what this map is doing. So a direction takes us somehow in this direction. So the lines are shifted towards the direction of A. Those lines got squeezed together, and for sure you see the angles will not be preserved. And if you apply, for instance, twice, so we'll move another deformation. That means you're moving in the direction of A all the time. If you apply several times, you can get one parameter family even of such things. If you do the ball, slash it in this way, you'll get disks, two-dimensional disk. And the transformation, a plane will go to a plane, so the disk will go to disk, but they will shift it. They will shift it into the direction of A. So you can picture this transformation, understand what they are. So now we'll show that the ball, admissible velocity ball, and that all the velocities which are allowed by the relativity is about the symmetric domain and the projective automorphism. You remember what we have to show. So it's a regular ball, a three-dimensional ball that we are used to see. And so for such a ball, the definition is you are considering all vectors in R3 which have length less than c, the ball of relativistic admissible velocities. Now, the automorphism group of D is the collection of all projective automorphisms of D. Remember, we have seen that the Lorentz transformation act by projective automorphism. They take the ball into itself, and therefore they generate out of D. Now, this is homogeneous. I will see why it is homogeneous. For if you pick up any point A and D, then the map V A of V, taking A plus V, what it happens to 0, if you take 0, you get A plus 0, which is A. That means you can move. This is automorphism. Is now D, this phi of A of V, and of 0 it gives you A. That means it is homogeneous. It can move the 0 to any point. Now you need only one symmetry. And the symmetry about the origin is a very simple one. When we send each vector to its negative, it fixes only the origin. And therefore, we have a symmetry fixing the origin, and we can move the origin to any point. Therefore, our domain is a bounded symmetric domain. That is a bounded symmetric domain under out D. Out D will be the automorphism of D of projective automorphism. The symmetry of A, which occurs in the definition, is very simple and understandable what it is. You have to perform in system K prime S0 to send each vector to its negative, and then observe this map from the frame K. Since the fixed point there was A, the origin, and now from our point, it will be the fixed point, it will be A. P of 0 is A. Therefore, you'll get an automorphism about any point in the domain, which is simply the automorphism in the regular automorphism A0, as observed in a frame where this frame has the origin has the velocity. Now, what is important for the automorphic group, one of the things that we use in the triple product occurred when we go to the Lie algebra. So we have to go to the generators of the automorphic group. Physically, the generators play even more important role. group itself is describing transformation of velocities, while the generators represent acceleration. And since the physical law deal mostly with acceleration, so it's very important to describe the generator. So the generators of boost, so we take this Einstein's velocity addition, and those are elements of our D, and there are also rotations. Rotations also preserve interval, and therefore the general group our D is a composition of a rotation and phi A for any A. It means that very specific form. The generators. So to define a generator, you have to take a smooth curve in the automorphism group, that means a collection of automorphism. Starting at S0, it is the identity. And you calculate the derivative of this with respect to S at S equals 0 for any point V. Since you know explicit formula for phi A, and you'll get the Lie algebra of which is small out of D, or of the Lie group capital out of D. In this particular case, it will be of the following form. Since you have two types, so for the phi of A, you'll get this expression, A minus the triple product VA with V over C squared, while on the linear one, in the three-dimensional space, generators of rotations can be given. Each rotation has an axis of rotation, and this is B, and so it moves any vector V, B cross product B, where B, the length of it, is connected with the angular velocity. So there's an explicit expression for the our D. You see it is polynomials of order 2 in B. This is linear, this is constant, and this is quadratic in B, and linear in A. Here we saw the pictures how those fields look like. Such field, this one is without rotation, without B is 0. That means you have the A. When you get close to the boundary, it dies out on the boundary, or it became tangent. If here it will become tangent. Because A is the direction here, so they got what is the condition? A vector field belongs to the Lie algebra in order to keep the boundary to the domain within itself. So on the boundary, it has to be tangent to the boundary. Now, if you have also rotations, then this is how the vector field looks like. Once more, you're on tangent on the boundary, but it has a rotation inside. Now what we want, it is not so convenient to work with this group. Why? It's non-linear group. The maps are in general power series, and we would prefer to work to have a linearization. And it turns out there is a linearization of this problem, of this group, if we go to Minkowski spacetime in Cartesian coordinates. Minkowski spacetime is the regular spacetime T, X, Y, Z, and we introduce new coordinates, x0, x1, and x2, x3 are the regular x, y, and z. And x0 is ct, yc, we put it in order to have all of them in the same unit. T was in time in second, and c is meter per second. Ct is meters, the same way as x, y, and z. Now we have seen in the previous lecture that there is an invariant metric. It means a metric which is preserved by the Lorentz transformation. It is ct squared minus dx squared minus dy squared minus dz squared. Or this can be written as the x0 squared minus the x1 squared minus the x2 squared minus the x3 squared. So to write it in the tensor notation, we introduce a tensor with lower indices, which is a matrix like on the diagonal we have 1, minus 1, minus 1. And we can introduce an inner product xy eta mu ni x mu y ni, which is bilinear, has a regular inner product, but not positive definite. In physics, positive definite is not more appropriate. ds squared that we define, which is written here, can be written the inner product of x with x, which is eta mu nu dx nu dx nu. So we can use those interval. If we go to the covectors, then you have to have a metric with the upper indexes. But for such a metric, this is self-invertible. The inverse of it is the same, because if you multiply on the diagonal, you get 1. Homogeneous Lorentz transformations are given by this transformation that we obtained in the last lecture. A linear transformation on M, preserving the metric. So here we call this group out M. Out of M will be similar as we had out of D for a bounded domain, but there we had to use affine transformation. On M, we'll use linear transformation, but not all of them. We're using the one which preserves the metric. Now, there is one-to-one correspondence between out M and out D, because any linear transformation, Lorentz transformation, preserving the metric, it defines you a transformation on the velocities. And reverse, if you know it on the velocities, you know what it is doing to the origin, and you can get the Lorentz transformation. So those are two equivalent groups. Now, in Minkowski space, we have different 4 vectors. The vectors, we call them 4 vectors because they have 4 coordinates in the light cone. So it is as follows. The light cone, what is the light cone? You have a point here, and you send flashlight in all the directions from this point. And where the light reaches, it goes by a cone because it promotes with the speed of light in all directions. So it's a section of this cone, a 2-dimensional section, a 3-dimensional. Really, we cannot draw the 4-dimensional because we are used to 3-dimensional space. But in general, it is a 4-dimensional one. And that's the light cone, where the light propagates along this cone. And we have all vectors on the light cone. We know them B0. They are satisfied that the metric B0 squared minus this is 0. That's exactly the condition that something propagates with the speed of light. And what we therefore, and since we know that light propagates with the speed of light, so they all propagate on the light cone, and they have 0 length. If you have a vector inside, that means a squared in this case. This part is larger than this, so the norm of this vector is positive, and the time component is positive. This is called future pointing time-like vector. B, this one is on the light cone. It's called future pointing light-like vector. B squared equals 0 because it's a light vector. And in order to be future pointing, you have to ask B0 to be positive. C, like a vector outside the cone, is called space-like vector. In this case, this part is dominating. And therefore, the metric which takes the square of this minus this will give you the negative. The space-like vector are negative. They present events which could not be reached from one to other. What happens in far-reaching star now it's not important for us, but we will know about it in the future. We can have path-pointing time-like vector, like here, which is inside the cone. Inside the cone, that means d square is still positive, the norm, and d0 is negative. Now the wall lines of something which moves, so it has to be inside the positive light cone in the future, and inside the past light cone in the past. This is true only for massive objects. Massive object moves always less than the speed of light. Light is composed non-massive, massless object, and therefore the massless one move on the light cone. Massive object move inside the cone. Now, when we have such motion, we have to replace the motion of velocity by force velocity. Force velocity is, you have to replace the velocity was the displacement, space displacement, divided by the time difference between the two events. Now, the time wasn't invariant between all the frames in classical physics. This is not the case in relativity. So we want to find something replacing the time, which will give us approximately the time when the velocities are small, but it will be invariant from one system to the other. So we introduce a notion proper time as an invariant time parameter. And we denote it by tau, and we define it in the following way. We had this ds square. Ds square was in units meters square. So we can write it c d tau. C is the speed of light, and d tau we want to have in units of time. So together they will give you meter square. So now they will be the same unit. So d tau will be in units of time. Now we write explicitly what's the ds square. Is this one c squared dt square minus, I wrote the x1 square plus dx2 square plus dx3 square as the r square. Now what happened? I take out c squared t square outside, and what I'm getting, 1 minus dr square over dt square is exactly the velocity, and we took c square outside, so we will get also over c square. So we have that the metric can be written as c square dt square times such expression. This tells you that the tau dt, we want to compare this and this, so we have to divide by this expression and take the square root. C square will cancel, so dt equals gamma d tau, where gamma is 1 over the square root, 1 minus v square over c square. We have seen this gamma in the Lorentz transformation. So when v is much smaller than c, so this is almost 0, the whole expression of the square root is 1. So gamma is 1, and the t became d tau, approximately. That means the proper time is invariant because the s is invariant, c is invariant, so the tau is invariant, and it is approximately equal to the time when the velocity is significantly smaller than c. So is the definition of the force velocity. we take the displacement between the two events, dx mu, and we divide them by the tau. It's like a velocity on the world line when the world line is parameterized by tau. We can do it the following. We can, first of all, x mu can be written this way. And we divide it first by dt and dt d tau. Now, dt d tau from here, you see it is gamma. And what you'll get here is c. And when you take when you differentiate this by t, you get c in the first place, and the x by the z by t is v. So we have a map for each v for velocity. So there's one-to-one map between the four velocities, which have this form, and the velocity v. What is the norm of this vector u? Okay, to calculate a norm of a vector, we calculate the norm of the square of it. The norm of the square is the square of this expression, gamma square. And for such thing, this norm is, see here, is the square of this one minus this, v square. Now we can take c square outside, and gamma square is exactly the expression you get here, 1 minus v square over c square, which you cancel with the gamma square, and you're left with c square. So all four velocities have the same norm, c. The four velocity itself has the norm c. So really, they form a three-dimensional manifold. All the four velocities are vectors, four vectors, such that from Minkowski space, that the norm of them is c squared. If the norm of them is c squared, you can go backward and you can find v. So that's nice description of the representation of the field of the three-dimensional ball D now became a three-dimensional manifold. Now the Lorentz transformations made this manifold into itself, because Lorentz transformation keep the tau, and so the x d tau, the norm is also preserved, and therefore this condition will be preserved. How they look like when we draw the picture only for one spatial dimension, we get u0 minus u1 square, u0 square minus u1 square equals c square. It's a parabola, hyperbola, and its asymptote are exactly the light cone. So u is the four velocity here, and the light cone is this one. Now, if you want to draw a three-dimensional picture, you once more have a hyperboloid, and you have a light cone in this way. So we have now a new way how to represent the velocities instead of three-dimensional and four-dimensional. Basis of this homogeneous Lorentz group. Now the transformations will be both in the x direction, which are given by the Lorentz transformation in this way, where beta is v over c, gamma is what we have defined earlier. We can change it to hyperbolic function quotient hinge by introducing psi such that tangent hyperbolic of psi is beta, because this over this, hinge over cos is tangent hyperbolic, it is beta, and we define psi this way. So really, it is some kind of hyperbolic rotation. If you want, the other part of the group are also generated by the rotations, and the rotations are given in this way. We take a rotation in the x-axis by an angle phi, and we can get the generators of them. Both of them, Vx and Rx, are rank 1-1 tensor, because they act as matrices on vectors, and the result is a vector, so they have to have one upper and one lower index. Their columns form an orthonormal basis in M. Here you have it cos square minus sin square is 1, and here it is minus 1, as supposed to be, because the orthonormal basis, the first one is time-like, and the other one is space-like. Also here, this is norm 1, this is minus 1, also here, those are minus 1. So, and they are orthogonal because when you take the inner product, and since the second one you have to change the sign, you get 0. And here the product, and both have the same sign, so it's possible you'll get 0. What will happen with the generators? How you calculate a generator? Your psi has to be now varying, and at 0 it has to be equal 0. We differentiate this. Your cos will become sinh, and sinh will become cos, and you're putting 0. So on the diagonal you get 0, off diagonal you get 1. So that's how it looks like. And the same thing if you do here, cos will become sin will become cos, and substitute get 0, you'll get 1 minus 1. All of them can be shown very easily that those form antisymmetric matrices 4×4. So now we want to define, as we have done in classical physics, after we had velocities, we had now for acceleration. For acceleration is, by definition, you differentiate the for velocity by this invariant parameter, because that's replaced the time, the classical time. Now, since u squared, which was that definition, is c squared that we have seen. So when you differentiate this, you get the derivative of this became a times u, and then you have another term. When you differentiate this, u ni, you get another one. That means you get both terms will be of the same type, eta mu ni, a mu u ni, which is equal 0. Why? Because when you differentiate this constant, you get 0. That means a with a lower index times u ni must be, the contraction of them is 0. It means in some sense, the acceleration and the for velocities must be orthogonal. This tells a very important consequence. If in classical physics we could talk about acceleration depending on the position in the field and independent on the velocity, now we cannot do it, because for any vector that you pick up, you can pick up a velocity which is not perpendicular. And this condition must be preserved always. Therefore, thus, A must depend on U. Very important consequence. Relativity taught us that we cannot more assume that acceleration will depend only on the position of the field. We have to assume that A depends also on the for velocity. Now, at this lecture, we'll assume the simplest dependence on the for velocity is linear dependence. Linear dependence, so it will be given by a matrix, linear function of U. So in order to become A has upper indices and U had upper indices, so it has to be a mixed tensor. Sometimes we'll talk about a lower index, then mu will be also below. K depends, the constant, depending on the properties of the moving object. So this is the form that we will discuss today when the acceleration has a linear dependence on the form velocity. So this, what it tells us, in this case, what can we say about this matrix? We can say the following. The definition is I started with this, which is eta mu, a mu, ni, u, ni. Now, this can lower the index of the ni, and you get a ni alpha, u alpha, u ni, has to be 0. Now, pick up any pair a and alpha and ni, then you get one term, alpha, a, u alpha, u, a with ni alpha, and the same term you get with the reverse order, alpha, ni. You get the same coefficient. They'll add up together, and they must be equal 0 because u alpha and u ni are arbitrary. So you get that a alpha beta must be equal minus a beta alpha, because the sum of them has to add up to 0. That means our tensor is antisymmetric. Antisymmetric can you define only when the indices are on the same level. So if you want to work with antisymmetric, you get then A automatically with a lower index. So this is antisymmetric 4x4 tensor, 1x1 tensor. How looks an antisymmetric tensor? So the generators of this group out M are 4x4 antisymmetric tensors, F on M. How they look like? Here, if the indices are below, it's antisymmetric. So here it's E1, so it's minus E1, E2, minus E2, E3, minus E3. Now we are left with 3 other indices, and we use the following notation. B1 is some kind complementary to this one. You see if you cut them. And B2 is complementary to E2, and B3 is complementary to E3. And if you raise the indices, that means you have to change the signs of these rows. What will happen? That this part E will become always positive, and B will still be an antisymmetric 3x3 matrix. Those components could be identified as the electric and magnetic field E and B. And why? Because this equation, which would be the replacement of Newton's law, mass times the acceleration equal the force. Here, for electric field, we have the charge alpha, which can be taken on the other side as the K, and then you have this tensor F acting on U. If you check what happens expanding this to the first order in V over C, you get the famous formula m dv dt equals q e plus 1 over c v cross b. This is simply substituting what is used through the velocity v, making all the calculation and taking only constant term and the first order of v. If you take only 0 term, you cannot get this one because the magnetic field can be felt only if you have a velocity. If you don't have a velocity, you have only the electric field, and then you get, for the electric field, you get only the first term. But if you want to move to another system, right away you pick up this magnetic part because such a matrix when B is 0 is not invariant moving from one basis to another. So if in one system you had a charge which was at rest, it has only electric field, the other system automatically it will give you a magnetic field. And that was one of the shortcomings that was in classical mechanics. And here we see how you overcome it very nicely. So this is if and only if. And so that can be taught also how your relativization of this formula. You take a classical formula and look how it should look in relativity. This has to be replaced by 4 acceleration. Parameter has to be replaced by tau. This one should become a tensor, and you identify it with this tensor, and really check that to order first order in V over C, the two formulas coincide, and this formula gives you all orders V over C, and gives you the right formula, relativistically true formula for the evolution of a charge in an electromagnetic field. Now I want to get another consequence. I want very fast repeat what we had in the lecture 4 in Newtonian mechanics. We have seen that the Lagrangian was in this way defined, and when you have a Lagrangian, the parameter was used time on the curve, and we got what was important. The LDXI is the force, and the LDXI dot is MXI with upper index, and it was defined the momentum. Now, it is a little bit problematic because I has an upper index, PI has a lower index. That's one of the shortcomings of Newtonian description, and you see it disappears if you do it right with relativity. The Lagrange equation we had this one, and which could be rewritten in the Newton's second law, and we had a problem. There's no physical meaning for the Lagrangian. Now I want to define the form momentum in relativity. Form momentum. Here's the definition. We remember the form momentum has to be the mass time the forward velocity, but we have to have it lowering the index. And in relativity, we have how to lowering an index. I taught you in the lecture on the tensor, you're lowering the index by use of the metric. And we have an invariant metric, eta mu ni. So this will be now well defined because such summation on ni will leave you on the index ni below, and you get p ni. When 0 is the rest mass. If we use the coordinate decomposition for momentum, you write it in the following way. For such a momentum, you write this is the vector part of the momentum. The time part of a momentum is energy over time over c. That's the meaning for the time component of the momentum. It could be written in the following way. M0 here, and this lowers down to make the sign -1. You had gamma C B, and lowering down, put a minus. So you see the vector momentum is now of the three-dimensional vector momentum is simply the regular M0V, but multiplied by gamma. It is very natural thing because V was the derivative by time, and multiplying gamma, which is dt d tau, which will make the derivative of the spatial displacement by the time tau, which is now the invariant time. What would be p square? P square, you have to take the norm of this, you get m0 square. This one, you get gamma square. And when you take here c square outside, you'll get gamma -1 square. So gamma cancels, and you get m0 square c square. Very important formula. That's for the momentum. The square of the momentum is similar as for the velocity, but it has this m0 square. The square of the forward velocity was c square, but the momentum is m square c square. Now, why is this the justification? Why it's energy? So let's write down what it is. So we know the vector part is m0 gamma v from here. What we get for E? For E, we will get here, C will go here, get m0 c squared, gamma. And this is called in the literature mc squared, the famous formula for Einstein, E equals mc squared. But you have to remember the m there is not the mass of the object, it is m0 gamma. And currently a lot of people don't use and for the mass this mass, they use for the mass m0, because that's a property of the object, not of its motion, how I observe it, and they use the gamma. So let's write down this explicitly, what is m0 c squared gamma is written down here. Now we expand this in the power series. At 0, the value when v is 0 is 1, so we get mc squared, and then the next term will be the power minus half, and the inner derivative will be minus 2v, and 2v squared over c squared, and now the c squared will cancel, and you'll get this formula, plus higher terms. All other terms will have c squared in denominator, v squared with c squared, and therefore they will be relatively small. This is a constant term, independent on the velocity, but this is exactly the kinetic energy. That means the energy of an object is like the energy when its velocity would be 0, plus the kinetic energy. Therefore, this is the right definition for relativistic energy. So this is the main formula, mc squared, justifying this, which really is m0 gamma c squared. And this term, m0 c squared, is considered the energy of any massive object. If it has mass m0, then it has like an initial energy, m0 c squared. And that follows from this simple observation for the momentum and the connection E to energy. Very important observation. Now, I want to explain you, this gives us an additional information, very important information, how to treat massless objects. It means objects which have rest mass 0. It means if you cannot keep those objects at rest. So how they exist if they have no mass? But they have momentum, and you can measure their momentum. For instance, one of such particles, the most famous, is photons. Photons are particles that light is built up of photon, and they have 0 mass. But they have momentum. You can measure it when it hits some very light things. It transfers its momentum to this object. So how it can happen? The momentum is written down here. And how can it be a momentum is not 0 and m0 is 0? So we can remember probably from calculus, the only way to get from 0 something non-zero is multiplied by infinity. So if gamma will be infinity, so m0 gamma may have non-zero value. Only that case, you'll be able to get a momentum non-zero. That means the momentum, the same thing for energy, in order energy be not 0. And if it is a 0 energy, once more it doesn't exist, and m0 must be 0. So the only way, gamma must be infinity. So if gamma is infinity, when is gamma infinity? Look at the definition of gamma, this expression. When can this be infinity? Only when v squared is c. That means any massless object must move with the speed c with respect to any inertial frame. If you pick up an inertial frame you have to pick up with respect attached to some massive object, and all non-massive objects, massless objects, will move with the speed of light. Very simple observation from the definition of momentum, and to be exist, you must have non-zero. So this is C, such particles, ds square, what will be? ds square, we had this formula, and if v square minus c over c square is 1, so ds square is 0. So the whole line of them lie on the light cone. The light cone was exactly containing all vectors which have length 0. And so they propagate on the surface of the light cone. So the massive object propagate on the hyperboloid of the 4 velocities, while the massless propagate on the asymptotic behavior like the light cone. Now we can use the previous formula for the momentum and the energy, but it turns out there is a formula for the momentum and energy, and the momentum is connected to the wavelength. So all those particles have a frequency, they're oscillating. And this frequency of the electromagnetic field, it has a frequency omega. The energy is equal h bar omega, where h bar is Planck's constant. And the momentum since p square has to be 0 is the same h bar k, and the k and omega are connected to make this p square 0. So totally different definition, because the velocity of them, all of them is the same, the speed of light, so you cannot use the previous definition with v, but it is somehow related to a different property of those particles. Interesting to find is the limiting process that will lead from the massive one to the massless. We have seen that the trajectories are really a limiting process. You can build up a right limit when the velocity of the objects moves to the speed of light. They act like massless objects. Even the equations are totally different. Now we want to compare the 4D relativistic dynamics equation with the 3D. In special relativity, they introduce us a 3D, but it is, I am showing you very briefly, because really, I don't think you have to work with the 3D. That's only historically the people try to connect everything to the 3D once more. The true way to work is in 4 dimensions, because there you have the transformation, you have the invariance, you have the metric, etc. So the definition, the 3D definition was the following. You, in special relativity, you replace the force with length, kept the same force as it was defined in classically, and you replace the momentum by the gamma v as we had m0 gamma v, the vector part of the momentum. Now it turns out to be a strange thing, because really gamma v is differentiation first by tau and then by t. You get a mixed derivative. Okay, but you can work with it. And then you can denote gamma v with denote w. So we can write the w dt, where w is gamma v. And there is the gamma factor can be translated, which is the t tau, can be translated into terms of w. It is different than with respect to v. With respect to v, the square root is the denominator, and it has a minus. Here it became a square root and a plus. Now, such thing gamma v is not limited. Gamma can go to infinity. So W this is called the proper velocity, and proper velocity is unbounded. So in some sense, we lost the geometry. Instead of having a bounded ball, now we have everything. And then the acceleration is the definition du d tau, and you will see gamma, you get the gamma d tau, and the W, what we have here, because that was the U, and you get the W d tau, and U is C gamma and V. Now, how we calculate this one? The gamma d tau, here is gamma written down. When you differentiate such thing, you get 1 over the square root, you get gamma, and when you differentiate this expression, you get twice W over C square, and you get C square here and W here. That's the first term, the gamma d W. Now, the gamma d tau is the same, the W dt, the gamma d tau. Because this is the same differential phase by W and then W by tau. Now, the W d tau, what we use is the W. So you write it down, you'll get W is gamma, the W d tau dt. We write it the following way. The W d tau is the W dt tau, which is gamma. That's only thing what we have done. Look what we got. We get a gamma in the denominator and the numerator. They cancel out, but we get W over C square, F over M0, because the W dt was assumed here, F over M0. So we know what is the first expression here. Now, when you do the W d tau, we use the W dt d tau, which is gamma. This is gamma, and this one is from this equation, F over M0. Now we can write down explicitly what is M0 times A. So M0 in all those places will go on this side. It will be du d tau, which is this, and the gamma d tau we found is W times F over C square, and we got another C here from here. So it became C, and the W d tau was the same thing, gamma F, and M0 went on the other side. So we got such expression. This can be written in the form, if you write this U gamma, C gamma and W, and you write F as a row and a column, it will be exactly the same expression. So this F will be multiplied by the W, and you get this expression, and 1 over C from outside, and this one will be multiplied by gamma, which is the, and 1 over C and C will cancel. So exactly the same formula as here. But this is a 4x4 antisymmetric tensor. And this is already the form that we use. So any three-dimensional dynamics equation can be turned in a 4x4 antisymmetric tensor acting on U, which is much easier. That's a linear map, and everything is well defined. And this is the 4-dimensional antisymmetric. But for the antisymmetric tensor, a very specific one with having zeros here. If you move to another frame, you'll get a general antisymmetric tensor, and you'll get the equation that we discussed earlier. So the 4-dimensional relativistic dynamic equation is really K, some constant depending. In this case, it is M0 times C. Du d tau equals a tensor, antisymmetric tensor acting on the 4 velocity. So if the frame is moving with respect to another frame, you pick up also the magnetic part in this place. This discussion, this derivation is from the paper of me and Scar, making relativistic dynamics equation covariant, explicit solutions for constant force. Those equations could be solved explicitly. Now I want to finish with a few open problems in this lecture. And the first problem is we have seen that the ball D in 3 and R3, the relativistic admissible velocity, can be mapped to a manifold U of the 4 velocity in Minkowski spacetime by one-to-one map phi that we have observed. And we have seen the ball D is a bounded symmetric domain under projective automorphism. And if you consider, look in my book, you have the, if you use symmetric velocities, that we'll do it in the exercises, this bounded symmetric domain became under conformal automorphism. So you have two ways how to represent this ball, either by projective automorphism or by conformal. Is U symmetric manifold? Since there is a map, we have seen phi mapping this ball into U for velocities. We have seen the regular velocities are mapped to linear one. Is this the conformal one? Have another representation. What are the maps that became a bounded symmetric domain? U became a bounded symmetric domain. The elements of our D became linear maps on M with flow preserving U are other analytic maps on M preserving U. Can they be classified? We will see later that the linear ones are not enough to describe all the fields. We need also quadratic. So there's a clue that probably the group is larger. Now, this can be maybe used ideas from bounded symmetric domains, where we're able, if you have a domain with nonlinear map, we have a way to linearization of them. For instance, the velocity that we discussed can be considered as linear maps with R to R3 by dr equals v dt. And this can be embedded into Minkowski space, which is R plus R3. And maybe going through this procedure, you'll be able to solve the problem. Okay, that's for today.
Thank you.
Bye-bye.
Thank you.
Bye, everyone.
Bye, everyone.
Bye.